Ladies and gentlemen, we're getting the mercury out again. Chapter 7. Little like chapter 6, but a little different as well. Here we are. Are you surprised that you end up, well, it's not quite end up, you, in the middle here, get an alcohol on the more substituted carbon? No surprise there. Mercury is a little different than chapter 6. It's still mercury 2+, but it doesn't have 2 acetate ions. That chemical does not work very well with alkynes. This is a slightly hopped up version of mercury, and it works better with alkynes. And mercury 2 sulfate and water and sulfuric acid. So it also looks like sodium borohydride is not part of the story here, and that is correct. The reaction is called, it's got the same name to start with, Oxymercuration. The demercuration is done with a proton in sulfuric acid, and they name it Protonlolysis. A good name, I like that. It says a proton is used to cut the molecule up. That's what lysing is, cutting. Okay? So that's what we're going to do. The protonolysis is here. This step here. And oxymercuration is clearly here. Once again, oxy, yep, and mercuration. Mercuration. Any surprises that they are opposite each other? They're anti? No, because there's a triangle, and what after you make your triangle, what's the next step every time? Backside attack, which generates anti. Good. In the chapter 6 reaction, the first step of the mechanism is to ionize the mercury. Ha! It's done for you. I've already got the ion written out. You don't have to generate the ion. Oh, nice. Attack the mercury 2+, and this time you used 1 arrow. There's no arrow coming back because metals don't have lone pairs to come back with. Please don't reinvent chemistry. Metals don't have lone pairs. All right. So this triangle will be the partial triangle. 3 partial bonds. Got it? Where'd they come from? Those old pi electrons in that 1 pi bond you just used. Please remember, you only used 1 of the pi bonds. You still have a full pi bond left, and you have a partial triangle all the way around. 1 of the plus charges still lives on mercury. The other plus charge is shared inside the triangle. That helps that plus charge a lot when you share it between other atoms. And then it's a triangle. You better do a backside attack on which carbon? It's always been the same. It hasn't changed. More substituted carbon. Only do the 1 arrow, please. There's no way to do an arrow on a partial bond. We don't even try anymore. And that's going to push your isobutyl over here. Your double bonds here now. Your water's over here. I made that a little big. I don't know why I made it so big. I know it looks like I flipped the picture upstairs. In fact, that's exactly what it is. The flip of this, isn't it? Except it is also the conjugate blank of what's in the box. What's my blank? This bottom one is the conjugate. The bottom one is the conjugate acid, has the extra proton, and this is the base. So I need a base. I need the best base that I have available right now to take this H off. And you might want to say water. I don't have hydroxide here. You can't ever have hydroxide in a reaction that has sulfuric acid. Please never try that. The result's the same every time. -1 impossible in this universe is the comment every time. Okay, you can never, in a reaction, if you have somewhere in the mechanism a strong acid drawn and somewhere else in the mechanism a strong base drawn, you will be losing a point, and one of those species cannot exist. How do you know which? Well, when I start with a strong acid, you are not allowed to draw any strong bases at all. Acid-base chemistry says a strong base would immediately react with your strong acid. You can't even make the strong base. Okay? So a lot of talk. But the best base available is one you might not think about. It's right here, up here. That ion it's the conjugate base of hydrogen sulfate. It's just called sulfate, right? Here it is. SO minus, O3 minus. Can I put a red circle around it so you know where it came from? Say, where's that come from? Well, it's circled upstairs. And do your arrow. Grab that H. Just an acid-base arrow, right? And for those of you who are into bookkeeping, O minus 3SOH is what you just made, right? And now the next step is the step where you're going to use a proton to cut off the mercury, and the mercury comes back as mercury 2+. I'm just putting into words what I'm seeing in front of my face. I'm going to use this proton to take this mercury off. I don't think I need to use this yet. And here's the arrow. In fact, it's an acid-base mechanism. And carbon, well, before I say anything, which of these two atoms, if that bond breaks, is going to hold on to the electrons a lot more strongly, carbon or mercury? 2.5 versus a metal. I'm not even going to give a number. I don't care. It's a metal. It's not 2.5. It's lower. Characteristic of metals, low electronegativity. That's why they're metals. So carbon keeps the electron and picks up a proton. Do you want to see the new proton? Here it is. There's the new proton. Wasn't there before. There was an old proton there. I'll show it. Old proton, old proton. Oh, I had it cis to the OH there. There you go. It's not very well drawn. You want me to put the blue one on the left now just to make it look prettier? There it is. Still awful. There you go. Old proton, new proton. Protonlolysis. And mercury 2+ is back to being mercury 2+. That's why I wrote meow, right? What's meow mean again? Meow means your teacher's a little strange, yeah. I used to have cats for decades, okay? I love cats. And yeah, the cat came back. He's scratching at the door, you know, catalyst, cat. And he doesn't need to be used anymore. Our new functional group is called an enol, and it's our new functional group of the day. Enol. New functional group. It's a combination of two functional groups, but it has its own unique behavior, so we have to learn it as a new functional group. Its name says it all. What two functional groups combine to make it? All, alcohol, ene, alkene. Alkenes don't like to have alcohols attached. They'd rather be a carbonyl. And the reaction's called tautomerization. Okay? So keeping in mind those H's were there just to show you the old H and the new H. We don't need to see them anymore. I just want to make sure the tautomerization mechanism is very clear. to do this new mechanism called tautomerization, that's the name, tautomerization, you need an acid-base pair. I think I have that over the arrow, right? Over and above and below the arrow is a hydrogen sulfate, the base, and sulfuric acid, the acid on the bottom, right there. So you need an acid-base pair. I have it. And the base is going to grab what atom? What atom does a base always grab? A proton. Oh, even better answer than mine. My question was in error. It doesn't grab a hydrogen atom. It grabs a hydrogen ion called a proton. Thank you. Which proton has to leave? Just look at the picture. Tell me which proton is gone so that I know which one to take with the base. The one on the alcohol. What happens to the sigma bond between the O and the H? Keep in mind, arrows flow into the next arrow, which starts, which flows into the next arrow, which starts. So what are you going to do with that sigma bond between the O and the H? Make a pi. It's called resonance. Resonated in. And what happens to the old pi? It breaks and picks up a proton. Nicely said. Where does it get this proton from? From the acid. Learn tautomerization like you're going to see it over and over again, everybody, because you're going to see it over and over again. You're going to see it even on the next activity. It'll look a little different, but it's the same arrows. The base grabs the H. The sigma between the O and the H resonates and becomes a carbonyl. Carbonyl. The old pi picks up a proton. How many H's are on the end of this stick? Right here. 3. How many H's were on the end of the same stick here? 2. Yeah, that's where the proton went. I didn't show it, but it's a new proton there. I could put a blue H there if you want. I'm not going. And this is our first reaction this semester we've seen that makes this functional group, right? Ketone. Anytime you have reactions that make functional groups, you have to learn them and group them. Add them to the story of ketones, which is just beginning in your life. It began when you learned how to identify one. Chapter 1. It continues now. Hey, I'm going to start a little chapter on just ketones that we know in Orgo 1. We know in chapter 1 what they look like, and we now know in chapter whatever chapter, chapter 7. Chapter 7, we know one way of making them. You will be adding many ways of making ketones as you go. It's all about organizing your thinking based on functional groups, which are the characters in this play called organic chemistry. And we have to know their nature, how they behave, and who they hang out with, and all that good stuff. Just pretend it's like a play. And I think that's the end of that mechanism. So you can start with this alkyne. And remember, there's 2 major kinds of alkynes. What are they? There's ones that are on the end of a chain, like this one. What's that called? A terminal alkyne. A terminal alkyne can be made into a ketone, is the take-home message from this overall mechanism. The chemicals needed are, see, here's your summary. We like it. Reacted with these chemicals, Hg, SO4, water, and sulfuric acid to make a ketone. There's your little summary in a nice square box. Yeah, pretty good square box. Okay. Terminal alkyne can be made into a ketone. And we'll close this activity. Here we go.